Hello everyone. In this example, we will be going over gears, and this example specifically talks about gear geometry. Now, at this point in the semester, we're introducing chapter 15 simply because gear geometry and the equations that govern it are sort of important to give you some critical dimensions that you need for part A, which is the force analysis of your term project. Now, we will go into a deep dive of spur gears later in the semester, but just to give you a good start on the project, we will just cover a few things on gear geometry. And it's just the first two sections in your textbook in chapter 15. So it's not a lot of material, just know where the equations are and what some of the variables mean and how you can determine some critical dimensions. So in this example, you have a pinion, which is the smaller gear that drives the bigger gear, which we call the gear. Now, conventionally, we just always name the smaller one as a pinion and the larger one as the gear. So the pinion has 20 teeth and has a diametral pitch of 8. That just talks about the teeth and the module, and the definitions of course, you can look up in the textbook. And the pinion rotates at 2000 RPM, so that's the rotational speed of the pinion, and that drives a gear which, as a result of their different sizes, that gear spins at rotational speed of 1000 RPM. And we need to calculate the number of teeth in the gear and the theoretical center distance along with the circular pitch. So right off the bat, we can tell that the gear is bigger just because both of them have the same pitch line velocity, or rather the linear velocity at the teeth is going to be the same. But because of their different sizes, the smaller gear or the pinion is going to make a complete revolution before the bigger gear in the same amount of time. And just from the ratios, we can tell that if one is spinning at 2000 RPM and the other one is spinning at 1000 RPM, then we can directly relate the diameters of the two gears. Now let's just write down what we already know. So for the pinion, then we know it spins at 2000 RPM. It has 20 teeth and it has a diametral pitch of 8. So P is the diametral pitch. And similarly, we know that the gear spins at 1000 RPM. We need to calculate how many teeth are on the gear, what the center to center distance is, and what the circular pitch is. So capital P is the diametral pitch, but little p is the circular pitch. And these are two different values. It's just a factor of pi that's different between the two, but they mean two different things. And again, you can look up what the definition is in the textbook. So let's go into the first part. Let's calculate the number of teeth on the gear, right? So what we know is that the gear spins slower. And if you look at equation 15.1, there is a relation there that tells you that the size or the number of teeth of the gears is directly related to the speed ratio of the gears. So just by knowing the speeds, we can tell that since the speed is half between the pinion and the gear, we can say that the gear is twice the size. And that's just by the relation that the ratio of the speeds, now little n here is the speed, is 2000 over 1000, which also tells us the differences in the size, which is directly related to the teeth, number of teeth, which is ng over np. So note that in over here, p is in the numerator and g in the denominator, because in the numerator on the other side of the equal to sign, simply because these two relations are inversely proportional. The smaller the gear is, the faster it spins. That's why. All right. So we know that the number of teeth on the pinion is 20. We need to calculate the number of teeth on the gear. So by this relation, ng is twice np, which is 2 times 20. So the number of teeth in the gear is 40 teeth. All right. So now for the second part, we need to calculate the center to center distance, or the theoretical center to center distance. So the reason we say it's the theoretical center to center distance is because here we make the assumption that the two gears mate at the pitch diameters or the pitch line. And so each gear has a pitch circle associated with it, and we assume that they mate at the pitch circle. If they don't, then the equations that are available in the textbook don't hold. And these are assumptions that are made in the textbook, and you need to be aware of these assumptions. So in equation, again, so this is the radius of your pinion. This is the radius of your gear. So we can simply say that the center to center distance C is equal to RP plus RG, which is nothing but half the sum of the diameters. And you will find this equation in your textbook as well. It's equation 15.1a. So now we need to calculate what the diameters of the pinion and the gear are. And we can calculate that by knowing the number of teeth as well as the diametral pitch of the gears. So from equation 15.3, you have the diameter of any gear equal to the number of teeth on that gear divided by the diametral pitch. Again, this is capital P, which is the diametral pitch and not the circular pitch. So if we're talking about the diameter of the pinion, it'll be the number of teeth on the pinion divided by the pitch. Now the pitch is the same for both, because that kind of talks about the module of the gear teeth, which has to be constant or has to be same between two mating gears. So this for mating gears, P is the same. And the inverse of P is M, which is the module, which is kind of the parameter that is usually specified. And M and P are just related by an inverse relation, where M is equal to 1 over P. So M is also the same. So the diameter of the pinion is equal to the number of teeth of the pinion divided by the diametral pitch. We know this is 20. We have this is 8. So this is 2.5 inches. Using a similar procedure, we can calculate the diameter of the gear, which is ng over p. That's 40 over 8, which is 5 inches. And again, like I said, the size of the gear is directly dependent or directly proportional, rather, to the difference in the speed ratio, or rather the speed ratio and the difference in the speeds. So we could also have said that the diameter of the gear is twice the diameter of the pinion. Again, this comes from the 2000 divided by 1000 RPM, which is 2 times 2.5, which is 5 inches. So you could do it however you want. You can use the equation for the first one, and then just by observation, figure out what the diameter of the other gear is if you know the speed ratio. And using these two values, we can calculate the center to center distance, which is 1 over 2 times 5 plus 2.5, which is 7.5 over 2. That's 3.75 inches. That is your center to center distance. And finally, we need to calculate the circular pitch. So this is denoted by the letter small p. I usually denote that by leaving a little bit on the top to show that it's the little p. So p and this is equation 15.2 that states the circular pitch is equal to pi times d over n. And d over n is simply 1 over p or m, which is the module. So I can say that this is equal to m times pi, or pi over p, which is pi over 8. And p has units of 1 over inches, or like 1 over distance, because module has units of distance. So that's pi over 8, which is pi over 8 inches, which is approximately 0.393 inches. So this problem basically summarizes all the equations or concepts you need for gear geometry, and you should be able to calculate any of the required dimensions you need for part A of the project. Thank you.